Greetings. The problem statement we'll be dealing in this audio slide presentation is the classification of liver and non-liver patients. The dataset which has been used is the Indian liver patient dataset. First, let us see what pattern recognition means. Pattern recognition can be termed as the discovery of regularities or patterns in data through the use of algorithms and the decision making based on these regularities. Let us see a few applications of pattern recognition. Loan or credit card applications. This involves credit worthiness classification using income, number of dependents, mortgage amount, etc. Document classification, which is based on the content and junk email filtering. This uses keyword-based classification of web pages and emails. One of the most important applications of pattern recognition is medical-based applications. This involves computer-aided diagnosis of cancerous and healthy cells. The classification is based on microscopic images of human cells. Another important application of pattern recognition is face detection. The algorithm learns by examples as to what a face is in terms of structure, color, etc. so that after several iterations, it learns to define a face. Supervised versus unsupervised learning. Supervised learning. This is an approach in which a training set is used to tune the parameters of an adaptive model. Each input in the training set is tagged with a corresponding target and the algorithm seeks a function from the input to the corresponding target. Once the model is trained, it can then determine the output for new inputs. The ability to categorize correctly new examples that differ from those used for training is known as generalization. If the targets are expressed in some classes, it is called a classification problem. Else, if the target space is continuous, it is called a regression problem. Example: predict the market price of a house given data about the size of houses on the real estate market. Price as a function of size is a continuous output, and so this is a regression problem. We could turn this into a classification problem by making our output about whether the house sells for more or less than the asking price. Moving on to unsupervised learning. The training data for an unsupervised learning algorithm consists of a set of input vectors without any corresponding target values. The aim is to find structure or relationships between different inputs and discover groups of similar examples within the data. There is no feedback based on the prediction results. The structure can be derived by clustering the data based on relationships among the variables in the data. Even associative memory is unsupervised learning. Example: clustering. From a collection of essays on a particular topic, find a way to group those essays that are somehow similar or related by different variables such as word frequency, sentence length, page count, etc. Associative. Doctors form associations between patient characteristics and illnesses with their experience. Based on a new patient's characteristics such as symptoms, family medical history, physical attributes, mental outlook, etc., the doctor associates possible illness. The classification problem. The goal in classification is to take an input vector and assign it to one of the k discrete classes Ck. The input space is thereby divided into decision regions whose boundaries are called decision boundaries or decision surfaces. Linear models for classification. Classification can be divided into two approaches: discriminant approach and probabilistic approach, which is further divided into two models: generative model and discriminative model. Linear models for classification. Discriminant approach constructs a discriminant function that directly assigns each input vector to a specific class. a linear discriminant approach for a two-class problem, the image can be seen. Probabilistic approach. Here we model the conditional probability distribution P Ck given X and then subsequently use this distribution to make optimal decisions about the class of the input. One approach is to directly model the posterior probabilities P Ck given X. This is called the discriminative model. Another approach is to model the class conditional densities P X given Ck for each class Ck individually and then use Bayes' theorem to determine the posterior probabilities. This approach explicitly or implicitly models the distribution of inputs as well as outputs and is known as the generative model. Classification versus clustering. In this slide, we could see two images illustrating the difference between classification and clustering. Now, let us see a description of the Indian liver patient dataset in brief. The dataset consists of 416 liver patient records and 167 non-liver patient records. It has 10 relevant attributes for each individual: age, gender, total bilirubin, alkaline phosphatase content, SGPT, SGOT, total proteins, albumin level, and albumin to globulin ratio. Our objective is to correctly classify if a patient is one with liver disease or not. Approach. We want to use the k-means clustering algorithm to group the individuals with or without the liver disease.
K-means is one of the simplest unsupervised learning algorithms that solve the well-known clustering problem. The procedure follows a simple and easy way to classify a given data set through a certain number of clusters, assume k clusters, fixed a priori. The main idea is to define k-centers, one for each cluster. These centers should be placed in a cunning way because of different location causes different result. So, the better choice is to place them as much as possible far away from each other. The next step is to take each point belonging to a given data set and associate it to the nearest center. When no point is pending, the first step is completed and an early groupage is done. At this point we need to recalculate k new centroids as barycenter of the clusters resulting from the previous step. After we have these k new centroids, a new binding has to be done between the same data set points and the nearest new center. A loop has been generated. As a result of this loop we may notice that the k-centers change their location step by step until no more changes are done, or in other words centers do not move anymore. The k-means algorithm takes k, which is the number of clusters, and a training dataset as inputs. Note that this being an unsupervised learning algorithm, no cluster labels are provided along with the training tuples. The k-means algorithm returns the centroid vectors of each of the k clusters it creates. To begin, randomly select k cluster centers. Calculate the distance between each data point and cluster centers. Assign the data point to the cluster center whose distance from the cluster center is minimum of all the cluster centers. Recalculate the new cluster center taking the added vector into account. The regular centroid formula we use in coordinate geometry is applied to find the cluster center. Recalculate the distance between each data point and new obtained cluster centers. If no data point was reassigned, then stop, otherwise repeat the process. In this diagram, A shows the original dataset. In B, random initial cluster centroids are chosen. The next four parts represent successive iterations of the k-means algorithm. Will the k-means algorithm converge? In most cases, it does. Let's define the distortion function j to be sigma I from 1 to m, nom xi minus mu c of I the whole squared. We can see that j measures the sum of squared distances between each training example xi and the cluster centroid mu c of I to which it has been assigned. The inner loop of k-means repeatedly minimizes j with respect to c while holding mu fixed, and then minimizes j with respect to mu while holding c fixed. Thus, j must monotonically decrease, and the value of j must converge. The value of k and k-means plays a vital role in the success of the algorithm with respect to proper separation of clusters. We need to minimize the number of clusters k as well as the average variance of the clusters. But as the number of clusters increases, the average variance decreases. Hence, different values of k need to be tested for a given dataset such that there is a balance between these two opposing factors. K-means is fast, robust and easy to understand. But a drawback is that the learning algorithm requires a priori specification of the number of cluster centers, or k. It is not guaranteed to find the optimal configuration. Due to the random initial choice of centroids, the algorithm does not yield the same result with each run. However, it gives best results when the elements of the data set are distinct or well separated from each other.
Now, here we have the results obtained by implementing the k-means algorithm. We have increased the value of k and grouped the dataset and classified it based on the number of liver patients and non-liver patients in a particular group. We can clearly see that as the value of k increases, the accuracy increases marginally. So, the right trade-off between number of parameters and accuracy is chosen for modeling the data. Here is another implementation of supervised learning algorithm on our dataset. We used a single layer neural network with dropout. Hence, now we can compare the accuracies between k-means and the neural network. Future scope. Supervised learning approaches for classification could be pursued as the dataset is large and is clearly classified into patient and non-patient classes. Example, backpropagation technique using ANN, SVM, LDA or PCA techniques. Fuzzy k-means algorithm could be used to allow every data point to belong to more than one cluster. Thank you.